Hello all, let's start verse section 6.8. 6.8 is about indeterminate form of limits and L'Hopital's rule. What is indeterminate forms of limit? In Calculus 1, hopefully your professor explained to you and you learn all rules of limits. What is limit? Actually, limit is right now coming back to us. After a long time, you deal with limits in Calculus 1, but right now we are dealing again with limits in Calculus 2. Limits is the basic idea of calculus, right? That's why it's very important to talk about limits. Before I go and show you an example, what is indeterminate form of a limit, let's do an example that you may saw in your Calculus 1. For example, if I give you the limit of x squared minus 1 over, for example, let's say x minus 1 as x approaching to 1. If you plug in, your professor definitely explained to you that the first step that you are dealing with any limit problem, you have to first plug in your number and see if it works or not, correct? Let's plug in 1 here. It gives you 1 squared minus 1 over 1 minus 1, which gives you 0 over 0, correct? If your limit is in the form of 0 over 0, or if you, after plug in, you end up with infinity over infinity, we call these forms indeterminate form of limit, correct? How to solve? Before you learn like a method or two methods to deal with these kind of problems. Remember, you can deal with this problem after you end up with 0 over 0, you say, no, I'll go this way. The limit of, you can factor the top, you can factor as a x minus 1 times x plus 1 over x minus 1 as x approaching to 1. Now, here you cancel, correct? And you end up with the limit of x plus 1 as x approaching to 1, which gives you 2, correct? Remember the first day or second day of calculus, definitely your professor explained to you that when you cancel a factor, it means your function has a whole. If you cannot cancel a factor, it means your function has a vertical asymptote. It's discontinuous and it has a vertical asymptote. But anyway, one of the methods were that if you can factor, remove the discontinuity, and after that plug the limits. But now, if I put an example, for example, if I ask you to do this, the limit of, let's say, ln x over x minus 1 as x approaching to 1, if you plug in here 1, it gives you 0 over 0 again, right? But the method that you learn in calculus 1, you cannot factor, or you cannot divide by the highest exponent of denominator, which was another method that you learned in calculus 1. You cannot do this. Then how to deal with these problems, correct? Now, I'll give you a general form, then I'll introduce to you the L'Hopital's rule, which makes your work very easy to deal with indeterminate forms of limits, correct? Let's say in general, if I have the limit of f of x, a function f of x, as x approaching to a, to a number, and it gives me 0, and at the same time, if I have the limit of g of x, as x approaching to a, it gives me 0, then the limit of f of x over g of x as x approaching to a definitely gives you 0 over 0, correct? Or if you have the limit of f of x as x approaching to a, if it gives you positive or negative infinity, and the limit of g of x as x approaching to a gives you also positive or negative infinity, then the limit of f of x over g of x as x approaching to a, it gives you infinity over infinity, which is a determinant form of limit, correct? Now, how to deal with these kind of limits if you cannot factor, if you cannot divide by the highest degree of denominator, then how to solve these problems or how to find these limits? Remember, if you are in determinant form, it means if you are in the form of 0 over 0 or infinity over infinity, after you plugged in the limit and you end up with 0 over 0 or infinity over infinity, then you can use this rule, which we call it the L'Hopital's rule. We write like hospital, but we don't pronounce S. We read it L'Hopital's rule. What L'Hopital's rule explains to you? The L'Hopital rules explains that if you have a limit of f of x over g of x as x approaching to a, it is always equal to the limit of the derivative of f of x over the derivative of g of x as x approaching to a. What does it mean? If I write this mathematical notation in an English language for you, right? The L'Hopital rule says the limit of quotient of a function, of functions, let's say of functions, is equal to the limit of the quotient of their derivatives. That's what we call the L'Hopital's rule. The limit of the quotient of functions. F of x over g of x is a quotient, right? The limit of f of x over g of x is equal to the limit of the derivatives of the quotient, right? It means f prime x over g prime x. This L'Hopital rules helps us a lot to deal with indeterminate forms of the limit, but again, I will put as a note here, note for you, only use if you have 0 over 0 or infinity over infinity. You can use this rule if your limit becomes 0 over 0 or infinity over infinity, which we call it indeterminate form. Right? Indeterminate form. Only and only if you have indeterminate form, you can use the L'Hopital's rule and easily you can find the derivative at the limit of the given function. When I am writing limit, let me explain something else to you that you should not do mistake later. When you are writing limit of f prime x over G prime X. Do not confuse this method with the quotient rule of derivatives. You are not applying the quotient rule here. Very simple. Take the derivative of the numerator and take the derivative of denominator. Do not use the quotient rule. It's not quotient rule. It's the derivative of numerator over the derivative of denominator, right? We call this one the L'Hopital's rule. Now I'll do like few examples for you to show how to deal with indeterminate forms of the limit. If they are, we call it usually type 1, which is 0 over 0 or infinity over infinity. Example number 1. Find limit of ln x over x minus 1 as x approaching to 1. Your first step, always, hopefully, I just told you that it was explained to you in calculus 1 that when you are dealing with the limit, your first step is to plug in the number and see if it gives you an answer, you don't need any method. If you end up with 0 over 0 or infinity over infinity, or later you will see 0 times infinity, or maybe infinity minus infinity, that I will cover all of them today for you, then you need to apply the rule, correct? Let's plug in 1 here. If you plug in 1 here, it gives you ln 1 over 1 minus 1. ln 1 is 0. And 1 minus 1 gives you 0. Oh, you end up with 0 over 0, which is indeterminate form of limit. Now, apply the L'Hopital's rule. In first 2 examples, even I will write the notation for you, but later when you do a little bit practice, you don't need to write the first step, correct? Then I can say the limit of ln x over x minus 1 as x approaching to 1, actually this one equals the limit of, let me do something else here for you. When you apply the L'Hopital's rule, do a little notation here because you end up with indeterminate form. Draw an arrow like this. Some people in your book, I think they put a capital H here, or some people they put like this, an L with apostrophe. It means now you are applying the L'Hopital's rule. It's really important to show this notation, because if you don't show this notation and immediately you take the derivative of numerator and derivative of denominator, people will get confused what you did, correct? Then it's better to show this notation. Now, I will apply the L'Hopital's rule. Its limit as x approaching to 1. What the L'Hopital's rule says, the derivative of numerator, it means d over dx of ln x, over the derivative of denominator, it means d over dx of x minus 1. You don't need to write this step if you get the concept that you are taking the derivative of numerator and the derivative of denominator. But in first and second example, I'll show you this notation, correct? Now, it's equal limit as x approaching to 1. What is the derivative of ln x? You just learned in 6.4 or in 6.5 when we were dealing with ln x. The derivative of ln x is 1 over x. The derivative of x minus 1 gives you 1. The ddx of x is 1 and ddx of 1 is 0. It means it gives you 1 minus 0, which is 1. Now, every time that you apply the L'Hopital's rule, the next step is to plug in again the number and check. If you are out of the indeterminate form, it's okay. If you are not, again, you do the L'Hopital's rule, correct? Some students, when they learn the L'Hopital's rule, without plugging here the number first to check, They again take the derivative and they go on and the answer goes wrong. Let's plug in. After each step, you have to plug in. Now, you plug in x approaching to 1. You plug in 1 here. It gives you 1 over 1 over 1, which gives you what? 1. Very easy method to deal with the type 1 in the indeterminate forms, which is 0 over 0 or infinity over infinity. Right? Let's do another example. Example 2. Let me see what example I brought here for you. Calculate or find or compute, right? Limit of e to the power of x over x squared as x approaching to infinity. Again, first step, plug in. It gives you e to the power of infinity. E to the power of infinity definitely gives you infinity over x squared. It means infinity squared, which gives you again what? Infinity. You see, you end up with infinity over infinity, which is a determinant form of limit. Now, what I do, I'll apply the L'Hopital's rule. Then I can write the limit as x approaching to infinity. The derivative of the top, again, in this example, I write the notation for you, d dx of e to the x over d dx of x squared. Limit x approaching to infinity. The derivative of e to the x gives you e to the x over the derivative of x squared gives you 2x. Now, if you plug in, it's the time again to plug in. If you plug in infinity, it gives you again infinity over infinity. Then what to do? Again, do the L'Hopital's rule. But which function? This one. Which limit? This limit. The limit of x approaching to infinity, d dx of e to the x over d dx of 2x. Limit x approaching infinity. Again, the derivative of e to the x is e to the x. The derivative of 2x is 2. Now plug in. It gives you infinity over 2, which is what? Infinity. Very easy, but you have to focus every time that you apply the L'Hopital's rule. The next step is to plug in the limit and check. If still you are in the indeterminate form, then again apply the L'Hopital's rule. Okay? Let's do another example. I think example 3, right? Limit as x approaching to 0, x squared over 1 minus cosine x. Step 1, plug in the limit. It gives you 0 over cosine of 0. If you plug in here, let me show you. It will be 1 minus cosine of 0, correct? Which gives you 0 over 1 minus. Cosine of 0 is 1. 1 minus 1 gives you 0. It means you end up with 0 over 0, correct? And 0 over 0 is indeterminate form. Then apply the L'Hopital's rule. Limit d, even in this example, I'll show you again the notation, but in next example, I will not write ddx every time, correct? The derivative of numerator, it means d over dx of x squared over d over dx or ddx of 1 minus cosine x, where x is still approaching to 0. Now, limit x approaching to 0. The derivative of x squared gives you 2x over the derivative of 1 is 0, correct? And the derivative of cosine x is negative sine x. But look, it's like this, 0 minus the derivative of cosine x is negative sine x. If you simplify, it gives you limit as x approaching to 0, 2x over positive sine x, correct? If you plug in 0 again here, it gives you 0 over. Sine of 0 is 0. It gives you again 0 over 0. Now, what will I do? I will apply again the L'Hopital's rule. Then I can write the limit as x approaching to 0, ddx of 2x over ddx of sine x, which gives me limit. ddx of 2x gives you 2 over ddx of sine x is cosine x as x approaching to 0. Now, plug in the number. You see, as soon as you plug in number, you have in the numerator 2. It means you are out of indeterminate form of limit because you got in the numerator 2, correct? And if you plug in 0 here, it gives you 2 over cosine of 0, which gives you 2 over cosine of 0 is 1. It means your limit is how much? 2, correct? Let's do one more example. I don't know which example is this, 4 or 5. I lost the track. Limit as x approaching to pi, 2 sine squared x over 1 plus cosine x. Again, if you plug in the value here, sine of pi, the sine of pi is 0. 0 times 2 gives you 0. Over, if you plug in 0 here, this should be 1 minus cosine x, not plus cosine. Cosine of 0 gives you 1. 1 minus 1 gives you what? 0. Now, in determinant form, then apply the L'Hopital's rule. Limit. This time I will not write the notation. X approaching to pi. The derivative of the numerator. You see here you have to use the chain rule. 2 times 2 gives you 4 sine x times the derivative of inside. The derivative of sine x is cosine x. Over 1, the derivative of 1 is 0 minus the derivative of cosine x is sine x, right? Negative sine x. Simplify a little bit. Limit 4 sine x cosine x over sine x as x approaching to pi. Before plugging, you have to check, you know, enough algebra right now. You see that if you can simplify your function, simplify, you see here I can cancel out sine x with sine x. Then I'll end up with limit of cosine x or 4 cosine x as x approaching to pi. Plug in the number, it gives you 4 times cosine of pi, which is 4 times -1, which gives you what? -4. Correct. All the examples that I did for you, they were in determinant form type 1, which is 0 over 0 or infinity over infinity. Now, let's deal with another type. Number 2, indeterminate products. What does it mean? If you have the limit of f of x as x approaching to a gives you 0, and the limit of g of x as x approaching to a gives you infinity, positive or negative, it doesn't matter. In this case, the limit of f of x times g of x as x approaching to a will gives you what? 0 times what? Infinity. This is the second form of indeterminate limits, which we call it indeterminate product. You end up always with 0 times infinity. How to deal now with these types of limits? I will put a short note for you actually here to explain how to deal with this. To find the limit of this type, convert the product of f times g to quotient, right? Easy. To quotient, it means what? Why change to quotient? To get 0 over 0 or infinity over infinity. What does it mean? Let's translate this. If you have f times g, you can change a product to quotient, correct? You can write this one as a f over 1 over g, some algebra, correct? Instead of g, can you write instead of g 1 over 1 over g? The right side and the left side is the same. 1 over 1 over g gives you g, right? Then instead of f times g, you can write as a f over 1 over g, or if you have f times g, you can write this one as a g over 1 over f. In any case, you are changing this one or this one, both of them are the same. You are changing the product to quotient. Why we are changing the product to quotient? Because look, if I have 0, times infinity. 1 over infinity will gives you 0, right? A number, a constant over infinity gives you 0. That means you will end up with 0 over 0, right? Or maybe infinity over infinity. That's the rule. This is what you should do. Let's explain it now in an example. Example number 1. Evaluate. Limit as x approaching to 0 from the right, x ln x. Again, your first step is to plug in the number. If you plug in 0 to x, it gives you 0 times ln of x as x approaching to 0, correct? If you remember the graph of ln, this is the graph of ln, correct? As x approaching from the right to 0, the graph of ln goes to negative infinity, correct? It means you end up with 0 times negative infinity, or you can say 0 times infinity, and one of the cases. You see, you are dealing with indeterminate form of 0 times infinity. Now, what to do? Change this product, which is x ln x, to quotient. How? Look, write your limit, x approaching to 0 from the right. You can write x over, let me show it to you. You can write x over 1 over ln x, or you can do this, ln x over 1 over x. Which one you should go? If you do this twice, that you will write x over 1 over ln x, finding the derivative of 1 over ln x is not that easy, right? But the derivative of x is easy. But if you do go for this choice, which is ln x over 1 over x, now you know what is the derivative of ln x immediately. It makes it easy. And it's easy to find the derivative of 1 over x. Then it's up to you. You have to take the decision which one you are sending to denominator, that still it will be easy for you to find the derivative, correct? Definitely you will go for this choice, which is ln x over 1 over x. You would write as ln x over 1 over what? X. Now, if you plug in here 0, again, it gives you infinity. The graph of 1 over x, as x approaching to 0, it gives you again infinity. You see, who remembers the graph of 1 over x? The graph of 1 over x is like this. As x approaching to 0 from the right, your graph goes to infinity. It means if you plug in here now 0, it gives you infinity over what? Infinity, which is a determinant form of limit. As soon as you are in the form of infinity over infinity or 0 over 0, apply the L'Hopital's rule. Right? L'Hopital's rule now. Limit x approaching to 0 from the right. The derivative of ln x is 1 over x. What is the derivative of 1 over x? The derivative of 1 over x is negative 1 over x squared. I'm showing it in this example to you, but I'm thinking this way, that from calculus 1, at least you remember what is the derivative of 1 over x, or you know how to find d dx of 1 over x. But I'll show you in this example because I just put here the answer. Let me show you. D over dx of 1 over x, or d dx of 1 over x. You can write this one as a d dx of x to the power of negative 1. correct? If you take the derivative, it gives you negative x to the power of -2. And if you change back the negative exponent to positive, you can write as a -1 over x squared, right? Which I put here the answer. These, I told you at the beginning of the semester that practice with your calculus 1, at least rules of derivatives. You should know it very well because we don't have much time, especially in this short-term course, to explain a lot of stuff from calculus 1, right? Now, before plug in 0, simplify if you can simplify. You can write limit x approaching to 0 from the right. Let's simplify this. It's a complex fraction. You can write as a 1 over x times, flip this one, -x squared. X cancels out with one of the x's. It means you end up with limit of -x as x approaching to 0 from the right, which gives you what? 0. Let's do one more example. Limit x e to the x as x approaching to -infinity. Again, if you plug in infinity here, it gives you -infinity or infinity times e to the -infinity. E to the -infinity, right? Or let's say first, if you have e to the -x, you can write this one as a 1 over e to the power of x. And if you plug in infinity, it gives you 1 over infinity in limits, which we call it what? A constant divided by infinity always gives you, because it's limit, your limit approaches always to where? To 0, correct? That means it gives you again infinity times 0 or 0 times infinity. Now, what to do? Change the product to quotient. Limit x approaching to -infinity. I'll keep the x. Instead of e to the x, I can write 1 over e to the x. Correct? And now you can apply the L'Hopital's rule. Excuse me. Then limit the derivative of the numerator. It means like this, d dx of x over, instead of 1 over e to the x, I can write d dx of e to the -x. Still x approaching to -infinity. Keep the limit, x approaching to -infinity. You see, in every single step, I'll write my notation. I write the limit, x approaching to infinity, and every single step, I keep it. I don't know how strict your calculus 1 professor was. I have no idea. I saw a lot of students when they're solving the limit problems, they don't care about writing limit. You do all the steps without writing the limit. And also at the end, they plug in the number. No one knows if it's a limit problem, right? You have to keep this notation. When you can remove the limit notation or the limit sign, when you plug in the number, only in that step, correct? Now, d dx of x is 1. d dx of e to the -x gives you -e to the -x. Correct? Let's simplify a little bit. Let's move this number up. Then you can write limit -e to the -x. If it goes to the numerator, it gives you e to the +x as x approaching to where? To the -infinity. And we saw that e to the x as x approaching to the negative infinity gives you 0. Negative 0, we don't have negative 0. It means it's your answer is what? 0. That was the second type of the indeterminate form of limit, correct? I will stop the recording here. I will do this lecture in 2 videos. And video number 1, you have type 1 and type 2. I'll stop the recording and I will do the rest, which is type 3 and type 4, in a separate video for you, correct?